So far it has been some really interesting keynote speaks, and of course we have saved something really special for you for the last two speaks, because this time it's not going to be two different speaks. They have merged into one special speak. So now it's 40 minutes of two speakers at the same time. That's really cooperation. So are you ready for that?
Yeah. I thought it would be 2 times 40 minutes.
2 times, yeah.
Yeah, we are ready.
Okay.
Yes, hello. Yes, it's also working.
Oh, sorry, I have to introduce you. We have Michael Weinhold from Siemens Energy and Jakob Østergaard, professor at the DTU Electro. So take it away.
Yeah, and I will kick it off. Very exciting times in the energy system, and several of the speeches before already addressed aspects that we will also dig into and further elaborate a little bit on. To put into context where we are at the moment in the energy system, it all started around about 160 years or so ago. Not a very old energy carrier being in use in our infrastructures. As a boy, when I was 11, I started tinkering around with electronics. Now I'm 50, so it's 40 years. 40 relating to 160, that's a quarter. That's quite a substantial time, isn't it? Wow. So it all started, AC, DC, war of currents, books, films were done about that. We built huge synchronous systems, we interconnected them. We built power plants, conventional power plants with efficiencies beyond 60% just in the electrical space. And then suddenly something happened, maybe 30 years ago, and I think the Danish were somewhat the origin of all this, the first movers. I have a DVD at home which depicts this grassroots development building wind turbines. And so you are sort of the nucleus of actually what happened here with these multiple stakeholders entering. So private people suddenly taking stakes and taking larger and larger stakes. And so not only multiple stakeholders, but now we also, and we will touch that, think in terms of multimodal energy systems, so crossing over into heat and chemicals. Very exciting times, and a lot of it also relates to the digitalization. Data is getting more and more important to organize all this complexity, but also innovation cycles shorten because that global swarm intelligence is connected via digital technologies and also applies them. So we will see shortening of the innovation cycles. Therefore, you see down here the time axis I had to alter a little bit. So especially those of you who are significantly younger than myself, very, very exciting times you will be in. And I also hope to be around for some time, and therefore I listened to the previous speeches quite closely. So an indication for how attractive electrical energy is, you see here, that's just the electrical energy consumption globally, rising with round about 3% per year. That rise will not be that much faster, because you always have to consider we need to build power plants to produce that electrical energy. So there is also some limitation in this ramping up. So you can sort of estimate it, for example, by looking what are the production facilities to produce power plants. But a lot is going on in the renewable space, and here the Danish, and Jacob will touch on that and show some numbers, are really global front runners in that field, especially of wind power. And a couple of years after the wind power deployment started, photovoltaics ramped up really, really fast. And there Germany is probably the world leader in PV deployment. This results in a lot of complexity on the power generation side. In our estimates, in the next, let's say, 15 years or so, as many power generation gigawatts will be installed than we have in total at the moment. But it will be different, the mix. We will have more and more renewables and more distributed power generators, so small scale, with variable output. And so it's also a lot about forecasting. Maybe today was easy, blue skies, but when there are cloudy conditions and the wind alters back and forth, or we have very strong wind conditions here in Denmark, you very closely watch what's coming in from the west. So this draws a lot of new stakeholders also offering services concerning forecasting, energy, weather forecasting. Weather forecasting used to be related to grill weather forecasting and sunbathing weather forecasting. Now it's energy weather forecasting. That's the name of the game. So when I want to see in Germany what the weather will be the next day, I don't go to the traditional weather forecasting maps. I go to the energy markets and see what the spot price of electricity will be on the next day. And then I see, oh, there's a solar dent on the market. That means a lot of solar at noon the next day. We have clustered the world in different regions because these things happen with different speeds, let's say. The common theme is more renewables, more decentralized generation, but different pronunciation. And so you see some color-coded countries, quite interesting. China, India, where close to half of the global population live. They do it all at the same time, central power stations and dispersed renewables, because they are energy hungry. Then there are the so-called traditionalists that are pretty heavy into coal and oil, coal and gas fired power stations, but there's also a lot of wind power being installed in the United States. So it's not really correct what we drew here on that map. So each region has its different story, and we are here in the center of green pioneers, we call them. That's these countries which ramp up renewables extremely quickly and also can cope with it, because there was no blackout in Denmark lately, no major
it's more than 10 years
but let's discuss it.
But actually, yes, we are right here in the middle, and you as a German and me as a Dane, we are actually in the very center of what is happening here. And so let's take a look at what's happening here in Europe. I think many of you probably know the European targets, the 2020 targets, which are very much driven by reducing the greenhouse gas emissions towards 2020. And one of the main objectives is to have 20% renewables in the energy system in 2020. And we have a lot of renewables available in Europe, actually, and different kinds. In northern Europe, we have a lot of wind power especially. We have a lot of biomass, and especially in the southern part of Europe, a lot of solar energy is available. There's also some wave energy resources, but I think the business case have to be developed to really exploit this in the future. And here you can see some numbers of the development of installed wind power and the solar potential in Germany. But perhaps, Michael, you could tell us a bit about what is the situation in Germany actually.
And this other map here is quite interesting. Maybe we go back, because from this map you would assume we do a lot of bio in Germany. Yes, we do. But we do almost at the moment as much photovoltaics as bio, because in the first 6 months of this year, we had a share of 27% of renewables in the German electricity sector, energy-wise, 27. 10% wind, 6% photovoltaics, and 7% bio. So photovoltaics is probably surpassing bio, let's say, next year. The reason is that if you have a given piece of land, you produce, if you use photovoltaic, typically 20 times more electrical energy than doing bio. In the region where I live, this is down here, there's a saying: if you want to have vacation, you do photovoltaics, otherwise you do bio, because bio you have to work a lot. You have to ship around the biomass, you have to dry it, and so on. So therefore, we not only have to think and where's the best potential for those renewables, but we have to think in terms of markets, we have to think in terms of acceptance, and as we will explore it a little bit further down our presentation, also about people, what people want, don't want. People now get into focus. I was trained in the 80s as an engineer. I didn't have any social science classes, zero. So I had to learn it all myself about acceptance, emotions, what people want and don't want. Yeah, let's look at where we are in Germany. And this was last year. I like these slides because they show, of course, in winter, not much solar. Sun is really low, even lower here. So probably you have less solar even, especially if there's snow on the panels. But typically very good wind power in winter. And at times, tremendous intake, as you see later in the month of January. But there are times when there is no wind and solar. And that's where the conventionals have to kick in. A solution could be if we would have a super grid in Europe, we could have a better balancing. Energy storage also is an aspect we will touch later in our presentation.
May I take over if you swap one forward? Because I think I can actually beat this.
Okay,
this is
good.
the picture here in Denmark. If we look at last year, the Danish wind power actually covered more than 1/3, or roughly 1/3 of the electricity consumption during the year, energy-wise. So it's really a high penetration of wind power. And actually, January this month, we had nearly 2/3 of the energy during January covered by the wind turbines. And if we look at a single day, actually the 21st of September, that was the first time where we had more wind power during a full day compared to what we consumed. So we really have a high penetration of renewables and have to have solutions to handle this. We also have situations where there's no wind power. If we look at the 11th of March this year, we only had 9 megawatt in average in generation out of the nearly 5,000 megawatt installed capacity. But actually we had some sun, luckily, that specific day. Nearly all the solar PV units generated power that day.
I used to say everywhere where you see plants growing on this planet, there's a potential for photovoltaics. It's just a matter of price.
Yes.
That's no wonder. It's a tremendous figure. Yeah.
So this is the picture we are heading here in Denmark, forecast of situation in 2020, where we'll have 50% wind power penetration in the electricity system. Actually, we are a bit ahead of schedule. We expect 60% in 2021. So it's really a lot of wind power in the system. And one of the major challenges of a system based on renewables is the balancing of the system. We have situations where we need someone to consume the excess power. We have situations where we need someone to produce, or we need someone to store the energy to swap it from one instant in time to another. But that's not all. We also need someone to deliver fast. We'll have a lot of very steep ramps of load and demand changing. So we need a lot of flexibility in the system. And if we ask the Danish system operator what is actually needed, they point on these three areas. We need strong transmission grids, super grids where we can exchange the different volatile production across countries. So we need the grids and we need the markets to do that. We need the internal flexibility in the system. We need demand to respond to the available energy. And we need a closer integration of the different energy systems. And then we need the smart solutions to tie everything together. So what we are looking into is, we believe, is more electrification. A lot of renewables, they are based on electricity. And we'll see electricity moving into the transport sector. We will see also heating solutions based on electricity, like heat pumps, to also absorb a lot of the renewables. and we'll see energy efficient houses that where the energy consumption for heating will become lower. And that means it becomes a more difficult business case for district heating and other water-based gas-based solutions. So they might also swap to pure electric solutions.
Yeah.
So we'll see a shift from an energy system where only a minor part of the system is based on electricity to a system in the future. Yeah, we forecast, several forecasts here in Denmark show more than 50% electricity in the system. And then everything will be bound together in a more integrated and intelligent system like this.
Yeah.
Does that fit with your picture?
I think these are very important trends that you outlined. And it's like two trends, electrification and digitalization, which actually accelerate each other. And so, of course, you need electric energy to run all these computers and so on. But you also this complexity also calls for analytics, for example, for forecasting and so on. And by having those tools available, this results in then even more usage of electrification. So complexity can be managed, and also, of course, innovation cycles shorten in the field of renewables, of wind power and so on, because you can simulate much faster, forecast much faster whether an invention will turn out into an innovation or not. So very important to energy carrier digitalization, very important two technologies. And I strongly encourage the students stay with electrical energy and also look into that data space. Now, we have moved very quickly, and we touched that before, from a system unidirectional. That was when I was educated. I think you were a little bit later. Probably you
but
were
still,
somewhat educated in between.
Still, yeah.
And those young people in the audience, where will it go? Where will it go? And there are strong indications, as Jacob outlined, that it will be more and more electricity based, because electricity is such versatile in application. Here you see those 4 clusters of innovation where we focus on, and they correspond quite nicely to what you said before, Jacob. It's smart grid. Smart grid is not only grids, it's a smart energy systems. It's that coordination end to end. It's that field of storage, and we will touch that in more detail, because that goes beyond just power into a battery and power out. It's flexibility. That's a very important point. A lot of utilities are now setting up new business models around flexibility to bring demand, to, for example, via virtual power plants, collect dispatchable load and dispatchable generation, bundle them together and bring them on the markets. And of course, grids. And the high end, that's the supergrid. And the low end, that's the nano grid. As private people, we live in the nano grid. And as energy system people, we also like to think in terms of supergrid to make optimal usage, for example, of resources that we have available. And also to share, for example, surplus electricity between our countries.
Yeah, I think actually there's one aspect in this picture that tied together, and that's the market solutions. And we believe very strongly in the market solutions here in Denmark, and I think in the developed world in general. But these solutions are actually challenged in the future when we have a lot of renewables. This is data from the Nordic energy market. Each dot represents an hour with a certain price in that specific hour and a certain predicted wind power penetration for that hour. And as you can see, there's a clear correlation. When there's a lot of wind power predicted for that hour, the prices goes to zero, and even we have negative prices in the market. So the conventional market-based model have to be changed in some way. And the markets have to be changed so the stakeholders get the right incentives to do the necessary investments that are socioeconomic optimal. And during operation, the stakeholders have to do the right dispatch of the system, which also provides the overall most socioeconomic solution. one of the, as Michael also mentioned and I touched earlier, one of the challenges we look into in the future is to create a more integrated energy system where the different energy infrastructures are tied closer together and utilized so the overall system becomes more optimized. And there are several solutions in this area. For instance, the heating and cooling systems has a lot of potential for providing storage for the electricity system to absorb a lot of this fluctuating energy. We also have on the consumer side, they might be able to shift between different forms of energy. That might be very cost-effective solutions compared to some of the more advanced solutions that we also investigate. If we can have the consumers swap between the different types of fuels and infrastructures, depending on the prices and the available of renewables in the different systems. But if you look at the really huge potential for storage, we move into to liquids and like methane and etc. But we also have different storage technologies and energy conversion technologies. And I think Siemens is working a lot on this, right?
This is one of the hot topics. And here we do not only have to think in terms of technology, but also business case. So no wonder that coming from a company, from an industry, we take a slightly different view, or we depict it slightly different, but the same message. So let's see, where do storage or crossover applications apply? If we go, let's say, from the central power station or central energy system where we historically came from, we were used to pumped hydro, maybe not here in Denmark. I think your largest mountain is 100 meters or so. So not that much pumped hydro here in Denmark, is there any at all? But for example, in the Alps. Now the problem is with the energy markets that you have more and more difficulties with pumped hydro power plants because the so-called spread between top price, lowest price on the energy markets vanishes more and more. The reason behind it is that renewables push down the price on the one hand side because there's always some wind and solar around. Solar not at night, of course. And from the lower level is put in because you have more and more flexible power plants, conventional power plants and flexible loads, which actually react when the electricity price gets below a certain value. So what you see on the electricity markets in Europe is that the bandwidth within the price actually moves, gets narrower and narrower. So they are having difficulties with the business case. Now, hydrogen is quite interesting because it's one way of crossing over into fuels. Actually, it's the first way of crossing over into fuels. And we do have electrolyzer technologies on the market, and PEM electrolyzers, which can be operated quite flexibly, are being commercialized. We do that ourselves. But here, of course, the question is, where's the business case? Yes, hydrogen offers to store away vast amount of energy because chemicals have substantially more energy than, for example, lifting mass. Just here, this example to make it more descriptive. If you want to produce 1 kilowatt hour, you have to carry 1 ton of water. That's 1 cubic meter, 400 meter high. That's 1 kilowatt hour. 1 kilowatt hour is the content of 100 grams of fat. So there are several inconvenient truths in that. One is that it's difficult to lose weight, and the other one is that if you want to store away vast amount of energy, you do have to move into chemicals. Somewhere in between, you have the batteries. There are different types of batteries, but according to our studies, and also what you see in the market, the main type of battery being deployed in the next years to come will be lithium-ion type of batteries. They are now in the process of cost-wise getting more attractive than lead-acid or lead-based batteries. And here you have to think strictly in business cases. Otherwise, you will not identify where they will be deployed or are being deployed. And what works probably within 1 or 2 years in Germany and probably also Denmark without funding is combinations of PV and battery storage. And then, as you mentioned, Jacob, that thermal. Thermal storage is quite cost efficient. It's very easy to store away vast amount of energy in hot water, but of course it's difficult to get back into electricity again. So once you're here, you're somewhat stuck here. But you can store away more than 50 kilowatt hours, for example, in a cubic meter hot water tank. And that's why, as depicted here, many municipalities running district heating networks are building now hot water tanks. Or in Denmark, you're using the soil. So there are all sorts of ways where water is contained. Even ice storage is being used, because when the phase changes, that's connected with a lot of energy. So bottom line, thinking about storage, not only electricity in, electricity out. It's not only a technology game, it's more a business case story. Just some examples. That's a battery storage system that we sell. We just delivered one to a factory, an industry factory in Germany, which need this container with around about 500 kilowatt hours of electricity stored for black starting the power plant in the factory. Here in that container, we have a PEM electrolyzer. We are building a 5 megawatt PEM electrolyzer system in the city of Mainz next year, and they will participate at the control energy markets with it. And very exciting topic is, besides crossing over into hydrogen, is that topic of producing high-value chemicals via the so-called carbon dioxide electrolysis. It sounds a little bit like science fiction, and when I first discovered it, I thought it would be science fiction, but we can prove it in the lab. And not only we, also Max Planck Gesellschaft is working on it. Basically what it is, if you run electricity through sparkling water, you can, through catalytic reactions on the electrodes, you can produce hydrocarbons. And you can tweak the process such that it's catalytic reaction and depends on the current waveform, that you can produce hydrocarbons where industry, here some figures, pay a substantial amount of money, for example, for ethylene. And also steel manufacturers are quite excited about it. Heinrich Hiesinger, CEO of ThyssenKrupp, just this week announced in a press article that ThyssenKrupp is also pushing very much for that topic. And now I believe with that swarm intelligence, that global swarm intelligence, I think this will happen, which makes electricity then even more attractive, doesn't it? Because then we may go even quicker, maybe beyond the 50% level also in Germany. So really exciting times.
And I think this is very aligned with the development that discussed here in Denmark. If we go to a 100% renewable-based system, we need solutions where we look into chemicals like these polygeneration plants. And the basic idea is that we produce electricity, we produce district heating, and we produce liquid fuels. And depending on the availability of the renewables, we can simply shift, and the need for electricity and heat, we can simply shift between electricity generation, district heating, heat generation, and liquid fuels if there's a lot of heat renewables available. So this is also an example of more integrated view. But I think it's also a challenging business case. But this is, I know a lot of researchers are working in this field also here at DTU to make this vision a reality. Another topic is actually to ensure a stable and reliable system. The electricity system is a huge, very complex system. And I think in future there will be a need for more real-time control and coordination. There's a lot of different stakeholders involved in operating this system. And when we have a lot of more renewables, we have a much more dynamic system. So we need these kind of solutions, and that's also something we are looking into here at DTU. We'll have much more converter-based generation that will create a lot of challenges. Today stabilizing synchronous generators, they are displaced by power electronic generation. This would challenge that will get a system with very low inertia. We'll have power system stability issues and insufficient short circuit power in the system. So we have to find some new solutions for that. But luckily, there's also some possibilities with the power electronics, because it gives us new controllability in the system. We have here at DTU developed, for instance, solutions where we let the wind turbines provide transient inertia response in the system, or provide frequency control. So there's also some new technologies that have to be developed in this area. Power electronics also move in the transmission system for long distance balancing of the system with DC connection, high voltage DC connections. And there we actually today has a lot of connections here in Northern Europe. Actually, Scandinavia is, I think, the region in the world where we have the highest penetration of these kind of connections. And there's actually a huge potential also for utilizing these in a better way. And I think that's also an example of how we have to have a more coherent view on the operation of the system. I have a very small example here with two systems, System A and System B here. There's two parallel lines here and two parallel lines here. The capacity of each of these lines are 100 megawatt. In the normal operation, you will have to operate with a maximum 50 megawatts on each line, because you have the N-1 criteria. So if this line fails, this will take all the load, the 100 megawatt. But actually you can, by using these HVDC lines in a clever way and coordinate the operation of those, you can actually increase the transfer capability to 75 megawatt of each of these lines. Because if one of these lines carrying 25 megawatts fails, this one will take over 100 megawatt, and then you can transfer 50 megawatts, which is transferred in this system and back here. So in a way, this is a very simple example of how a bit more intelligence can actually improve the operation really a lot. And another example is that I think we need also in the future with more power electronics, new, better ways to interoperate systems from multiple vendors, especially if we move to meshed DC networks. That will be really a challenge. So we need to have new validation methods. And actually here at DTU we have a world-class laboratory which are actually capable of doing some of these validations through a real-time simulation and hardware-in-the-loop experiments. So that might be an area for future collaboration.
Yeah.
And what are you doing in this area?
Actually, here you see such an HVDC system that we put into operation in San Francisco a couple of years ago, already 4 years ago. The reason that we did that was that San Francisco has a rising electricity consumption, but no space to build a power plant. So you need to make an electricity connection. They needed 400 megawatt additional power, which is quite a lot. In Germany, it would be sufficient for a city for 400,000 people living there, 1 kilowatt per citizen. So they needed 400 megawatt, but very limited footprint available. And the resulting technology was that new type of power building block technology, which for the power electronic enthusiasts among us, like myself, is a fascinating technology, which we are only now able to control because of the complexity in it. We can produce almost a pure sinusoidal out of the silicon. And that's a game-changing technology. We also apply that for connecting offshore wind parks. and talking about supergrids and multi-terminal, that's also being discussed in conjunction with the offshore wind parks now sprawling up in the North Sea. So just think about connecting all these neighboring countries and the wind parks via multi-terminal HVDC systems, and you can shift around power where it is needed. Technology-wise, a lot is there, almost everything is there, so let's do it. Of course, the conventional power plants have to react to it. They are now operated much more flexible than before. We did not only build the most efficient combined cycle power plant, but this power plant can ramp up and down within less than 30 minutes. So there's a lot of research going into the materials, and I will not talk about additive manufacturing because this also goes into it, at least at the moment in rapid prototyping. And I really want to see also that we will build those blades with additive manufacturing tools to even further push efficiencies and flexibility.
They tell us that we have to hurry up, so...
But we ignore it.
Yeah, let's do that. We have to go through the last 89 slides, right?
Yeah.
Another area that is very important when looking into renewable future is the cost of the renewables. If society shall afford this, the cost have to come down. And this is a very hot topic. If we ask the largest Danish energy company, Dong Energy, the cost have to be reduced with 40% within a very few years for these large offshore farms. And we also think can contribute with a lot of research activities in this to bring down the cost. And an example is using superconducting materials for generators for wind turbines, and this is actually a more costly technology. So how can that improve the cost? Yeah, actually you can make more lower weight and lower volume generators by using superconductors. Thereby you can make larger and more efficient wind turbines. So overall you can actually get a better business case with technologies like this. Another example is to have a better test and validation before going offshore. It's very, very costly to tune and to go and repair stuff when you have installed the wind turbines on the sea. So new solutions for test and validation, I think there's also huge potential for that. But you're also in the wind business in Siemens, isn't you?
And a close linkage, of course, to Denmark here. So this is a 6 megawatt wind turbine. Actually, we put it on land to test it first. This also relates to what you said before, easier to test. And if you look at it closely, you see that there's a lot of sophistication that's into the aerodynamics of the blades. Direct drives are now rising in usage, reducing complexity and cost and weight of the nacelle. So a lot of innovations. Not the end yet. We do machine learning to squeeze out more megawatt hours out of the wind turbine. Also in the future, a wind park will be controlled as one generator and not the wind turbines individually. And there were also topics like smart service and a lot of innovation fields here in that field. And yes, this is one of our major portfolio elements.
Yeah, the last area, which I think is extremely important for the business and for the stakeholders involved, is the decentralization of the energy system. Here in Denmark, today, more than 50% of the generation capacity is installed in the local distribution grids. In the recent years, 30% of the large centralized power plants has shut down. The Energinet DK, the Danish transmission system operator, forecasts that additional 20% will disappear within very few years. So this completely changed the game. Of course, it's also a technical challenge to operate a system which is highly distributed, and a lot of research are addressing this. How can we utilize the decentralized resources as an active component in the grid? A lot of this is done in a collaboration between Siemens and DTU. I think one of the main challenges is to have cost-effective solutions. But I think, again, you have to think a bit out of the box, combine with other products, look at the consumer as in a broader perspective. So a lot of things are possible to develop in this area. But there are also certain conflicts in this. The transmission system operators, they are concerned about balancing the system on one side, and the local distribution companies, they are worried about overload of their grids, of voltage profiles, and so on. This is things that happens in real time, and this is something that develops very slowly. So the kind of technology that these guys want into the distribution grid is actually slightly different from the technologies that these guys want in the grid. So there have to be found some new solutions that actually combine these two aspects.
Yeah, and now we enter again that, let's say, that visionary part, and I plan to talk about 2 hours about it, but I will not. I will shorten it a little bit. So we were coming from a centrally set up power system, and now suddenly within the last, let's say, 30 years, we have more and more of these distributed systems, so-called microgrid type of structures with local generation, storage, additional loads like electric cars connecting. And now the topic that is being discussed more and more are beyond the microgrids or below the microgrids are the nano grids. That's actually where we live. And that's also gives an indication that we have now more and more social topics in the energy domain. What do people want? What do they not want? What do they accept? What not? This means that engineers, latest from now on, have to understand how people tick. They have to understand social aspects and social implications. Otherwise, you will not have that innovation on the market. And this is a very fascinating area because it means that as engineers and scientists, we now have to work multidisciplinary. And for me, that's a lot of fun because you also learn a lot. As an engineer, you now learn beyond electricity. You learn chemicals, you learn social sciences, you even read laws. So fascinating area, and I encourage everybody among you to become an electrical engineer and help us work on the future. Yeah, I will end with this one. Thanks a lot for listening to us. Thank you.
Thank you to Michael and Jakob, and thank you for not completely ignoring me. And how can you stop such enthusiastic persons? I mean, you have so much energy when you tell about this. I really love that. We are about to close, but before we do that, we like the final thoughts from you. And I really like to facilitate the diversity. So I will invite again that you stand up. Can you please stand up again? Final time. It's late in the afternoon, so it's probably nice to stand up. And again, could you, all of you from Siemens, could you please put a hand in the air? Okay, because now I like all of you from Siemens to make sure that you get together with someone from DTU. So could you just move around, 2 and 2? Yes.
Also in that development. And for us as an industry, it's extremely important to work together with such a great university as DTU in order to also explore a little bit what's ahead. It's like you're like an extended radar screen for us. What you do, for example, in the Power Lab DK is very important because it's actually a window into the future, but it's happening. It's happening. So what you're doing here is probably a couple of years ahead what we will see then throughout our infrastructures, not only in Europe.
And we're actually also working together on using the Danish energy system, which is a couple of years in front of the general development in the world, to use it as a really large lab for investigating some of the solutions needed for the future. So, yeah.
Okay. Thank you. Some other thoughts? Okay, then I think we can all agree that it would be so nice with a cup of coffee. Christina, you want to say? I, 10 minutes break for coffee and ice cream, and then we'll be back. So thank you to all our speakers.